The graphite core in each reactor weighs approximately 2,000 tons. It is made up of individual graphite bricks, each 8 inches square by 2 feet 6 inches high. It is laid in 11 courses to form an upright cylinder 40 feet in diameter and 26 feet in height. In June 1960, the first graphite was laid in number 1 reactor vessel. Within the reactor building, clean conditions were strictly enforced, and all operators passed through security-controlled change rooms before they were allowed to enter working areas. Once accepted and logged, the graphite bricks were conveyed into the vessel by skip and hoist. Access was provided through one of the 6 gas outlet ducts, which will connect the vessel to the top of a boiler. Except those of the outer vertical edges, there are channels for the location of fuel elements, control and absorber rods, and to allow the flow of coolant gas. The whole graphite structure is carried on bearing plates and ball races, which allow for differential movement between the graphite and the steel supporting grid. Between each layer of graphite are tiles, one for each block. The tiles maintain the position of the channels in the layers of graphite relative to each other. Circumferential restraints, positioned at tile level, maintain core stability. An additional stabilizing precaution, used to counteract shrinkage of the core, is the use of zirconium pins, which maintain the lattice pitch and shape of the core. The side reflector graphite is located by dowels in the support plate and serves the purpose of throwing back neutrons into the core. This gas seal, at the base of the core, ensures that the coolant circulated by the blowers passes up and through the core channels and does not escape on the outside. The gas flow to the channels is controlled by adjustable gags, and in this way, the flow through channels in low flux regions is restricted to raise the gas outlet temperatures and thereby maintain a high average value for all channels. The magnesium alloy fuel elements are stacked 8 high in a channel and are self-supporting. There are over 2,500 channels, and the natural uranium charge weighs nearly 240 tons. On the reactor operating floor, much progress has been made. The top biological shield had been poured around the standpipes, and the first of the 2 charge-discharge machines, one is kept on standby, had been erected. The reactor is charged and discharged of fuel on load from the top. The machine can also handle control rods and other equipment. The height of the charge machine is about 55 feet. It is supported on a gantry running on rails across the pile cap. The machine itself runs on the gantry and can be positioned accurately over any one of the 256 standpipes on the reactor vessel. 88 of these are for refueling purposes, each standpipe serving 34 channels. The remainder are for control rods, fission product detection equipment, and other mechanisms required to be inserted in the reactor. Inside the heavily shielded machine is space for new and spent fuel, a charging chute for insertion into the reactor vessel, and radiation shielding plugs. The standpipes are each fitted with a power-operated valve, and it is through these valves that the machine connects to carry out its operations. The machine is remotely controlled and is equipped with a closed-circuit television system. Spent fuel from the reactor is discharged by the machine into a cooling pond common to both reactors. After a suitable decay period, the spent fuel is dispatched to a processing plant. Now we are back in one of the blower houses of number 1 reactor, where all work has been completed and the equipment proved. It is November 1960. Number 1 reactor has reached its final stages. In 1961, fuel will be loaded and power will be generated towards the end of the year. Already, carbon dioxide is being pumped in liquid form into its storage tanks. In number 2 reactor, all the boilers are installed, as are the blowers. The reactor vessel is complete and graphite laying is finished. We'll leave the reactors and go to the turbine house. This is how it appeared towards the end of 1960. But in early 1958, we had only just finished the erection of the main steelwork. The steam from the boilers in each reactor is led through underground tunnels to the turbine house, where the turbines were already taking shape in 1959. The rotors were being installed in number 1 set, and the remaining 5 sets, each a 52 megawatt rating, were in the course of manufacture. There are 2 major rooms in the turbine house. The auxiliary turbine hall, which will contain 3 low-pressure sets, each rated at 15.2 megawatts at 3,000 RPM, to supply variable frequency supply to the reactor gas blowers, and the main turbine hall. Here, one of the large condensers is in its early stages of construction. Water is drawn from and returned to the River Blackwater for the condensation of steam after it has passed through the turbines. Driven below the bed of the river are 4 concrete-lined tunnels, each 9 feet in diameter and approximately 300 yards long. 2 tunnels take the water from the estuary to a pump house for distribution to the condensers. The other 2 tunnels are outlets. All 4 tunnels emerge at a barrier wall, which is positioned in the estuary at a point where sufficient cooling water is available at all conditions of the tide. The wall ensures also that the water discharged from the station does not mix with the incoming cold flow. In early 1961, the cooling water system had been commissioned. It was ready to supply water to the condensers for the 6 main and the 3 auxiliary turbo alternators. Opinions vary on what forms the heart of a nuclear power station. A physicist would say the core. He's probably right. But for me, it is the control room. It is from here that the complete station will be controlled. These are control rod sector panels, which control nuclear reactions. And these are the bus and general purpose controls. The generator and boiler panels. It is not difficult for anyone with imagination to enter a room like this, quite empty and silent, and anticipate its activity. Of recorders tracing, and control room staff watching carefully the output, the changes in flux, the temperatures. Bradwell has been designed for maximum inherent safety in operation of all components. The control rods can be adjusted singly or in groups to compensate for flux variations in any part of a reactor core, either by automatic control or by an overriding manual control. The turbine system can be automatically controlled as a frequency-sensitive system. The station will operate on the national grid in the same way as any conventional power station. And so I come back to my office, to the paperwork and the discussion, to plan for tomorrow and the next day, and for the months ahead before the station is on power. You've seen some of our activities here. Quickly, we've covered nearly 3 years of construction in a mere half hour, from 1958 to 1961. We've shown you the big things, but there are countless hundreds of items, each important, that we could not possibly cover in such a short time. The completion of the graphite in both reactors, the burst slug equipment and installation of control rods, the commissioning tests, the first charge of uranium fuel. All of us here on this site have a pride, and I think a reasonable pride, in what has been achieved. 1961 will prove the fruits of our labors. For then, one of the two reactors will be on power. As for me, well, for the next few months anyhow, I'll be driving down that bit of winding Essex road to Malden, my home, and back to Bradwell, the place where I work.